All right. Everybody back? Everybody know everybody here? Anybody missing? Obviously, no. Yes. Are you missing? Okay. Yeah. So we're gonna spend a little time talking about going over GDB. Usage of GDB, also talking about how pondals can be used for binary exploitation and making your life a lot easier. So this is just a very dumb, simple program. Obviously bad, like Josh said, this is not going to be secure because we can just write arbitrary amounts of data into this buffer, and we're it's so kind. We even have a function up here, so we don't even need to actually we don't need to write any shellcode or anything. We can literally just redirect control to this give shell function, and we will get a shell. If you're not using GDB, this all looks fine. Eventually, if you just mash on the keyboard enough, you'll see we do get a seg fault, and I'm sure people have seen that before, even working these. But GDB is debugger. How many people here have actually used GDB before to some extent? Okay, so almost everybody. So really quickly for the people who haven't. So debugger is just a really easy way to see what the program is doing, breakpoint at certain places so you can introspect the program, see register state, see memory state, all that kind of stuff. So if we just type R, same as run, you can just R and then we can run the program, and this does the exact same thing. You can see if I mash on asdiff a little bit, we get hello asdiff back out. And then it says, okay, yeah, the process exited normally, nothing really weird happened here. However, if we run a mash on this keyboard, instead of getting the segmentation fault that we got before, you'll see, well, it's a little bit small, but in this case, GDB has basically said, hey, I see this is about to die, this program has gotten a seg fault, and so I'm not going to completely terminate it. I'm just going to break here and show you everything what the program is doing at this point. So this is also, you'll notice, instead of having the normal GDB prompt, this says pondebug. This is usually it's nice. Sometimes it breaks things, but it's usually a nice GDB basically extension or plugin, you can think of it, that just does it makes it a little bit easier to see what's going on. Let me hop out of this and show you what normal GDB looks like. So if we mash on the keyboard again, so this is what normal GDB looks like. You can see it's just it died here. It doesn't really show us anything immediately. We can still get all of this information. If we want to get information about the registers, we can see all of the register state. Or if we wanted to look at the stack, we can also do that, but we have to type that in. It doesn't just show it for us. So pondebug is a nice thing to have. You can just Google for it if you want to use it, or we can also put a link up somewhere. But yeah, so again, if we go back and we look at this crashing input, you can see this says we received a signal segmentation fault with this address, because you can see RIP, the instruction pointer, is now way up here, which that doesn't look like program space, right? If we look at the disassembly of this, so you can type main, you can see most of the addresses are down near this hex 400,000 range, which is standard for 64-bit programs. But we faulted with IP up in 7F00 some. That's weird. In this case, this is actually, well, everything is broken. We don't even have a backtrace at this point. But yeah, so let me just kind of go through some of the commands, I guess, at this point. So as you just saw, GDB can disassemble entire functions for you, assuming that you have symbols in the program. If you build a program locally, you're probably going to have symbols. If you get a binary from us or from a CTF, it's sort of hit and miss. Usually, most of the time, the easier challenges, usually the really easy ones won't, and then you have sometimes some that do, especially if there's a really weird function that it's not part of the challenge, so they'll just leave the symbol in saying this is what it does. But in our case, since we just compiled this locally, we have symbols, and so we can just say disassemble main or disassemble give shell and see the entire disassembly. Obviously, this is not like Binge's graph view, but it does give us just a linear disassembly. So one question that is, what do we do if we don't have symbols? So we do have an address though at the very least, right? So if we don't want to drop this into Binge, or if we're at some weird place in memory where like say we were doing Dora or something and we want to see what the disassembly is, we can't really see that in Binge because the function that we're in may have been like mutated by that XOR. So if we want to just see what the disassembly is for a given address, you can do X, which stands for examine, slash, and then you can say some number of things. So in this case, we'll examine 10 instructions worth of data at, let's say, this address. I need a space in there. And so now you can see, in this case, we've gotten our disassembly. It's the exact same as above, except there are more than 10 instructions here, so it's actually just continued down in the main, because apparently they're right back-to-back in the program. But yeah, so this is super useful if you just need to see like what code is if you don't have symbols, or if you're in some weird space that's been mutated and you don't have an easy way to like replicate that in Binge. So this X instruction is actually probably the thing that you'll end up using the most. If you just X something, it actually defaults back to whatever prior specifier you last used. So if you do X/10I, the next time you do X, it will use instructions. But you can also use X/10X to show you this as words, or D words, I guess, in this case. I guess I think those are actually size of integers. Or X/10A, which will show it to you as addresses. So this would be 64-bit. Or if you want to see strings, you can do X/10S. Or, in this case, it doesn't really make a lot of sense. Or X/10C to see individual characters. Or there's a lot of them. But most of the time, what you really care about are strings and some number form. So X or A, depending on what you want to see, addresses or just numbers or integers. So we can also use GDB if you want to just kind of do like math on things. If you need to find some offset, say, you can use P, which is just print. So we can say print, 0x400 whatever plus hex 10. It's really not a good calculation, but they'll show it to us in decimal. So you can also use this just for like quick hex to decimal conversions. And you can use the same format specifier. So you can say P/X to show you the number in hex. So it's very useful if you just need to do quick conversions. Also, as we saw way up top, GDB is aware of the register state inside the program, right? So if we need to get an offset from a register, we can say print as hex, R10 plus hex 10. And that'll show us the value of R10 plus hex 10. Registers are always prefixed with a $sign. That's just how they do it. And you can also, if you have symbols, you can also actually use this to show like full types. So if you have like a struct or something, you can actually view like all the struct members and everything, and GDB will print it out nicely. However, you very rarely have like full structure symbols in a CTF, and I don't have a structure in here, so I can't really show it anyways. But it is very nice to work with. Let's see. So we have examine, we have print. With pwndebug, you can see you can just type registers to view all of the registers, or if you don't have it, you can just do info registers to basically get the same view. You can also do another very common thing is if you need to see kind of like where things are in memory, you can use info process memory or info process mapping, and this will show you basically the start and end address and then what each thing corresponds to. So you can see our stack is labeled down here, our main binary is loaded in up here, This is all libc stuff that we don't really care about right now, but it's super useful if you need to find, like, you know, where did an mmap return, or where's my heap, or where's my stack. This also actually brings up a good point. In GDB, your stack is actually always going to be at the same place. So if right now my stack is at 7FFFDE000. If I quit and go back into GDB, run it, and I guess need to make it crash again, and show the mapping again, you'll see it's the exact same. So GDB actually disables address space layout randomization for the program that it's running, which is good but also bad, because it can make some exploits actually like seem like they work, but then they don't work remotely, because either you have like a hard-coded stack address that just happens to work every time in GDB, or you get really unlucky with, like, you know, GDB has a new line in like an address that you need to get at, because that's just where it chose to put the program every time. So, you know, this is what GDB does, but this is not how programs run externally. We can actually show the software. So if we just run overflow normally, and let me overflow. So if we actually look at what is it? Oops. This is too small. This is sort of the same, but you can see now if I like just running the program normally, the stack is definitely different, right? 7FFDD9613 is not 7FFFDE. Yeah.
Where did you get that?
Yes. So pgrep is a really useful utility where if you basically give it like the program name, it will just return all of the process IDs for that, like, that match that. So in this case, there's only one program on my computer named only one process on this VM running called overflow. And so it says, okay, that is PID 54676. And then in Linux, there's this magic /proc directory where if you go to /proc/ whatever PID you have, there's a lot of information about the actual process that's running. So we can get, you know, maps is the most useful for us here. However, you can also see like environ, not ls. You can see the entire environment that, like, the environment variables that the program is running with. You can also see like how it was executed, literally just what commands there are on the command line. That's not what I wanted. What else is in here? Yeah. Mem is weird. You'll probably never need it, but you can also, this is actually nice. There's this prog pid fd folder, and so that will actually show you what file descriptors it has open, and you can actually you can just echo stuff into these, and it will make it look like it was typed from standard in. So as of this, you also shouldn't really ever need this, but if I actually say let's echo asdiff into this process's 0th file descriptor, which is standard in, you can see it looks like I typed standard in over, or it looks like I typed asdiff over here, right? But I didn't. It just appeared. Whoops. Let's minimize this so I can actually get the other window back. Yeah, that's more or less everything that you'll need for our. CWD. Yeah. Okay. Yeah, so CWD is actually a symlink to the current working directory of the process, which is really useful if you're on a remote server and you need to figure out where you are. You can actually if you can read out proc self. I guess that really actually wouldn't work, but you can read stuff out of this since it's a symlink. So we can read cwd overflow.c. Since I'm CD'd into CTF, that's my current working directory. So there's our overflow program, right? This is just magically linked to wherever the program is running from. This proc self comes up a lot, not even just in binary exploitation, but even I've used it before in web exploitation too, because if you have no idea where your scripts are, but you have an arbitrary file read, you can read proc self, command line, cwd, whatever, and get a lot of information about where your program is running, what exactly is it, where is it running, information about it, like what version of things you're running and all that, and it's super useful. But again, for our purposes, the main thing we care about is proc self maps or proc PID maps, because that will show us, if we can read this on a remote server, well, we can now look at the entire, we can look at the entire memory mapping for that program.
Remember how when I said everything in Unix is a file?
Everything.
I really meant everything. Like
Everything.
Information about the running processes is just a directory.
Just a file.
With a bunch of files in it.
Yep. So, that's not what I wanted. All right, so let's go back into GDB a little bit, and let's try and exploit this program. So, dot slash. So, in addition to just having the R, you can. This basically acts as if you're typing it from Bash, as if you're typing the program name from Bash. So, if I did R as diff, this would set the first argv sub 1 to asdiff. You can also use it just like we did, and triple arrows to basically push into standard in from a string. So I can say, do that, and you can see that's taken this string, pushed that into standard in, and then the program runs with that as my name, right? But let's see a little bit more about what's going on. Let's kind of go through the Stack Overflow that Josh went through on the board earlier. So there's B or BR or literally anything that says breakpoint, or not even break, just you can break on a function. So if you have symbols, again, this will just automatically figure out where main is and put your breakpoint there. Or if you don't, you can also take an address and then break star on hex or the decimal representation, some representation of the address, and this will do the same thing. For our purposes, though, again, we have symbols, so it doesn't really matter, but again, a lot of times you won't have symbols, or you might just want to break into something that isn't just a nice function. You might want to break into where you jumped into in Dora, say. So you could break star on the corrupted function, and see what it looked like right before anything was running there. But regardless, so we've broken into main, and let's now just run. And you see we immediately hit the breakpoint, right? Because this breaks at the very beginning of main before the first instruction in main has actually even executed. So you can see at this point the backtrace shows we just got out of libc start main, hand wave that away for now, and we're in main. This is what our stack looks like. Here's the code that we're just about to run, and here's our register state. Super nice stuff. Another really useful thing with Pwn tools is that instead of, if I just manually ran info registers, instead of having to just manually be like, oh, this looks like a stack address, that looks like a stack address, that looks like program memory, that looks like program memory, it will actually just automatically highlight them for us, right? So it'll say, yep, anything in red here is code, anything that's yellowish color is stack, blue is heap, or whatever, color codes it up here for us too. So it's a really nice plugin again. But now say we wanted to just step through the program, right? We wanted to take this one line at a time and see exactly what it's doing. NI is how you do that, which stands for next instruction. And so you can literally just use this over and over, and you can see up at the top, we're just stepping through instruction by instruction by instruction. This also has the benefit, instead of some other commands, where if you hit a call, it will just it'll run the call and then break when you get back to your function. It won't step into the call, which can get really messy with libc. But again, we can run this throughout the entire thing, all the way through out of the program. This is super useful if you're like, where is this data getting set? Why is this happening? What is my register state here? And you just need to step through the entire thing. It's super nice to have.
I saw a call and I wanted to get into it.
Yes. Yes. So if we run this again, and let's say we go all the way down, and we hit this call, and let's say we do actually want to see what this call is doing. SI basically stands for step in. So we can step into this gets call. And so you can see we're now at this weird gets at PLT thing, and we're jumping into this really weird address, and we can follow that one. And another useful thing is if it can, Pwn will actually automatically, like before the jumps are even taken, it'll show you where it's about to go with those arrows on the right side. Or on the left side, I guess. So you can see at this point, we don't know where we're going yet, but it's automatically figured out, oh, we're going somewhere into libc, right, with the 7FFF address. And sure enough, if we do follow this all the way in, we do get down to libc. And now we're in mess of libc. Let's hop out of here. Q is for quit, or Control D, or anything else like that. Yeah, so let's break main again, run again, and now let's run with some input coming in. So let's run with just a few A's. If I counted that right, that should be 8. So, oops, break main, then run, and now we can step through. Gets will automatically go through. And now you can see we have the register state right after this. So you can see gets, again, the result of the function gets is stored in RAX. And again, Pwn debug is being really nice, and it's saying, hey, this address on the this address on the stack is pointing to a string hex 414141, and it's even showing us that's, hey, that's all ASCII printable. Let me show it as a string for you. So if we do this, not much is really interesting. We can see also this also shows up on the stack diagram down here. One thing that is useful to note, this shows the stack almost upside down, where you can see the low addresses are at the top and the high addresses are down here. It can make debugging easier, and it can also confuse you. So just like be aware that the low addresses are at the top in the stack frame, otherwise things don't make sense. Again, the stack goes down normally, so you'd expect the A's to be down here, but they're not, they're up at the top. But this does have the nice benefit of, if we run this again with one extra A, and we step through to get to this call, you can now see this, it follows a more like logical view of writing stuff. It goes left to right, down the page, basically. So it may make it a little bit easier to follow that. But back to actual pwning. Like I said before, this is just like having a shell, so we can actually run like subshell commands in here. So we can actually use Python or whatever else you want. And let's let's just print exactly 32 A's, because I don't want to type that out because I'm feeling lazy. We'll step through. And now you can see this ... It's like Pwn debug is saying that's all A's, right? Everything from this address on, it's A's, repeats 32 times. You can also see this stack address now has the low 2 bytes as 0, or the low byte as 0, versus before it was at 30. So we've overflown stuff. And if we do this again with 8 more A's, actually in this case, let's actually make it something different to illustrate the point. So we're going to throw 32 A's, then 8 B's out. And I'm actually getting tired of breaking or stepping through every time. Del BR1 is just short for delete breakpoint 1. So we can now set another breakpoint at this address right after gets, and then just C is to continue until this. So we're now here, and now we can see, okay, RBP is now B's, right? So if we step through to the end of the program, we come back here, and now in this, like, we're back in libc start main, but here RBP is now B's. And I believe there's at least one place in here where we try and dereference something RBP relative, and so you can see eventually we do crash. In this case, we're trying to dereference RAX, and that's 0. That presumably RAX got popped off the stack somewhere, and since we corrupted the stack, that just failed and fell apart. So let's go one more step. Again, I've disabled stack cookies for this, so it's, you know, we don't have to worry about any of that. Let's add 8 C's. You can see we get the call to gets comes back, and right now, right after the saved RBP is now CCCCC. And if we continue, we'll see right here. PumDebug is saying we're going to try and return to this address, which is obviously no good, right? 4343, as we can see here, it's not mapped into anything. So if we try and step through that, we'll get a seg fault, and we can basically be like, hey, we're trying to return to this CCCCCC address. That's no good, but this does mean we have control over our return IP, right? This is good for us, bad for everybody else. So another useful thing that you can do with the P command, we can say, let's just print the address of GiveShell. So, whoops, /x, P. And you can see it says, like, right here, boom, there's GiveShell. We don't even actually have to have a, oops, sorry. We don't even actually have to have a disassembler for this. We can do all of our disassembly right in here. And now, you know, now we just need to get to this address. We just need to set IP to this address. So we have a couple different ways we can do that. Let's just start off with the simple one, which is we're just going to manually type in our backwards hex encoded stuff as a string literal, and that's actually enough. No, it won't be. Let's just fill out enough null bytes. One more thing. Okay, so we're now printing 32 A's, 8 B's, and then this address, which again is just the little Indian version, so you can see there's B6. Actually typoed there, that should be 05. And then 40,000. And if we step through this, now when we return, invalid address. Why are you giving me an invalid address? Did I typo this again? GiveShell B605400000. That should have worked. Interesting. How is that happening? Oh, I didn't continue it with enough zeros, it looks like. Right, this is a problem actually. So what's happening here, is actually gets, or I guess actually it's probably more likely that the shell interpreter is in here. It's basically saying, I see a null byte, and I'm just going to interpret that as end of string, and it's going to basically just stop taking my input. So you can see we did get this 4005B6, that we got that part of it, and we got a null byte after that, but the high 2 bytes of this were not actually overwritten. However, I believe if I ran that outside of it, that worked before. And, oh, whoops. Print A times 32 plus all of that. Okay, and I'm missing a quote. Where am I missing a quote? Oh, because there's... Okay, so we're still seg faulting there. So let me try something else. Does the triple, does that not work with null bytes? I thought it did.
That should work.
Yeah.
You can do.
Let me try just putting that into a file. Interesting. That's bizarre. We got null bytes. Interesting. Regardless, so just gets terminated on a null. And that's fine, because they'll just overwrite nulls past the end of it, right? We can overflow further than we want. We just can't not... We have to send it enough nulls, but we definitely have plenty here. Does gets just stop at a null byte now? That's a new one.
See what ends up after gets.
Yeah.
Bugging.
Yeah, actually, there you go. A perfect example of
Are
debugging.
you debugging or debugging are bugs? Or just bugging?
Oops. Let's run. Interesting. Okay, so this should be immediately after. Yeah, no, it's just ending on the null byte. Interesting. Let's just see if this. So this obviously will give me an invalid address. However, that. Did I typo something? Yeah, I put an extra 0. That would do it.
So this is XR.
Oh, that ate up my quote somehow.
Slash OXO1 at the end. Or actually multiple
Yeah,
places.
multiple places. Derp. Okay. There we go. That looks better. Yeah, so you can see we still have that 0, 1 here. However, it looks like gets is now just stopping at a null byte. That's
Yeah.
that is interesting. Regardless, yeah. So this is the basic premise, though, right? So we're running our program. We can just throw whatever arbitrary input. Python's useful, super useful for this because you can just like construct these byte string or these strings just by saying I want this character this many times, this character this many times, etc., etc. And it's also this technique is very useful where if you don't want to bother trying to figure out like how much space you have to fill exactly, you can just say like give me 8 Bs, 8 Cs, 8 Ds, 8 Es, 8 Fs, 8 Gs, and then just basically see where your registers end up. It's surprisingly effective because you can just do that once and then be like, all right, so I need to pad 32 characters and then this one's IP, and then you're done. You don't even have to crack it open in a disassembler. In this case, though, we have exactly 32 bytes on the stack for our buffer, and then we immediately have saved BP and saved IP. It's weird as I thought I had that working earlier, but regardless. Let's see. So yes, now what if we want to do this in like a more repeatable way? As like if we're developing a longer exploit chain, we don't want to have to be like entering this weird string of GDB commands every single time. We want to like debug this program as we're like progressing through our exploit. So this is where PwnTools, the Python library, comes in useful. A lot of you have used it already when we were doing, I guess, potentially even more recently. When we're doing like socket things, because it makes you can just like connect to a remote and then send and receive on that. You can receive line, you can receive so many bytes, you can do all that kind of stuff really easily. However, PwnTools is not just for sockets, right? You can also do all kinds of other stuff with it, and it's super, super nice too for binary exploitation stuff. So let's just start. So from Pwn import star, so everybody's probably seen that one before. But instead of creating a remote, what we want to do this time is let's create a process called overflow. And if we just run this right now, you can see we start this local program, but then it immediately stops because the script is, we aren't telling it to do anything. It's starting the process, and then Python's exiting, and so it's taking the program with it. However, this process is just like the remotes earlier. This is what PwnTools calls just a tube. It is a thing that you can send and receive from, which is really nice because when you're developing an exploit here, you can do all of your send lines and then some receives or whatever. And then if you want to do this on a remote server, all you have to do is just change this process to remote, and then give it whatever port and host name, and then everything will just work as it was before. You don't have to like save the output of this to a file and then like enter one line and then manually receive and transcode stuff, and you can just, everything is a tube, so you can just say this is now a remote instead of a process as it was before, and it's all good. But in our case, all we need to do here is actually just send a line, right? We just need to send input to it. So again, we're going to send 32 A's, and we're going to just send up some B's to fill the buffer, or the return RBP, the saved RBP. And then, as Josh noted earlier, there's some really useful pack and unpack things in here, functions in here. Probably the most used is P64, which basically stands for pack 64. PAC64 bits. So you give it a number, so let's say P64 late, and it will take this, flip the endianness around, and then put it into a string, so you can just concatenate it with all your other strings, and it'll just be there. You don't have to worry about encoding or using struct.pack or anything like that. You can just plus P64 or whatever. There's also P32, and then there's also U64 and U32. P32 should be self-explanatory. PAC's a 32-bit number. And then U32 and U64 are also really nice if you have like a leak of an address in memory. You can just say U64 this address, it'll flip the endianness around again, and we'll decode it as a number. So you could just like U64, if you know where your stack is, just U64 that address, and then you can just add numbers to it, right? It's just a number in Python. But for our cases, all we need to do is encode a number, since this is where we're trying to jump to. Let's see, if we do this right now, oh, and then there's also .interactive, which will basically just make this just a terminal, essentially, where you can just type into it and it'll send it and it'll receive automatically and that kind of stuff. Sort of like what you would expect from Netcat. But you know what we get here is it runs, but again, this lead, that's not a valid address, so it's going to crash. And this got EOF while reading is basically how PwnTools shows you that. It says, I lost the connection to either the remote or to the local process because it crashed. So this is obviously not what we want to see. And sure enough, you know, if we actually exit out of PwnTools, or if we exit out of the interactive shell, PwnTools says, hey, yeah, this process stopped with exit code -11, which is a seg fault. But there's, you know, locally you have GDB. And this has, PwnTools has a thing where you can literally just .gdb, and you can even give it like a sequence of commands to run in the GDB, like on GDB's command line. So in this case, we don't want it to do anything, but if we then just say Python this, .gdb, is it GDB of P then? Right. If I can type .attach. So now you can see we run that and GDB automatically springs open and it's set up, it's broken in right before anything has really happened. Or in this case, it's actually broken in a little bit late, to be honest. It's broken in when we're waiting for input. But regardless, GDB is open. Again, we could have actually told this to automatically run GDB commands. So if we want to set up like a list of breakpoints to automatically stop at, or if we just want it to like automatically continue, or anything else like that, we can completely script GDB from that, and it's very nice to use. But regardless, this is also nice because once we continue, now it looks like it's working. Why, I don't know. But you can see we're now faulting at leet, which is, you know, what we were looking to do earlier, but except not with leet, with giveshell. So, you know, that's nice. Hop back in here, and in this case, there is actually a way to get PwnTools to load a binary and then give you the symbols for the binary. So you could literally just do like, here we'll do it. I believe it's executable. So this is basically saying just load the program. Don't run it, but just like parse the file format, like the ELF file, so that we can get symbols out of it. We could just it's the capital F. Oops. I don't personally use this one a whole lot, but it's nice. So. Yeah, now if I Python on here, I do. Oops. Yeah, so you can actually use e.symbols, and we could say give shell, and let me actually comment the rest of this out and just print this out. So if we run this, you can see it's actually loaded the binary, and it's also told us some nice information about like what protections are enabled. But more importantly, it said here's where giveshell is located. And if we take this and like we just open up GDB on it again, if we just print giveshell and then look at this as a decimal, you can see they're the same, right? So this has done all that for us, and So now all we need to do is just go in here, and then we can just encode as a 64-bit number the symbol, the address of give shell. And now, here, if we run this, what has failed there? Oh, symbols. Whoops. That is actually one thing to note. Since GDB attaching is done asynchronously, like you tell it to attach here and then it does sometime later, you can get errors from GDB, which just like they're sort of unintelligible. Eventually, you'll find something in here that basically says like it's essentially saying I can't open the program, like I can't figure out where things are. This basically just means the program's crashed, usually because there's something bad in your script. But yeah, so if we run this again now, hopefully that looks better. So we're now waiting for input. We can continue, and now you can see GDB has also told us, hey, the program over there has actually started a new program, in this case dash, which is the interpreter. So we now have a shell, right? And imagine this were running remotely. We can cat flag or whatever, but in this case we can view source and ta-da, we have a shell running. So yeah, this is super nice to kind of not automatically, it's a really useful tool to help create scripts for binary exploitation challenges, especially ones that are complicated and that take multiple hours to develop these, because you can reuse this and you can run it and then just say run until you get all the way down to where I currently am, and it'll reproduce the exact same thing every single time. And then you can like just break into GDB wherever you are, or you can try out new code, whatever you want to do. It's super nice. Let me actually bring up some examples from challenges that I've solved before. CTF solutions. This is going to be a little bit small, or not too big. Let's grab one from... yeah, ACES is not the best example. Let's go into DEF CON calls. Those were good. So, like, here's a script. This one's 60-something lines long, and you can see it's the exact same thing, right? That's also really tiny. I'm sorry about that. It's the exact same thing, though, right? You can see even up here, it's so nice because you can just say, this is a process, develop on your process with GDB, and then say it's now remote, and it'll do it all on the remote server, just the same. But in this case, you can see I'm setting up a thing to like leak a stack address, and then you have to do some other stuff. And then, again, it's just Python, so you can do all of your computations and stuff relatively sanely. In this case, I'm constructing a ROP chain. We'll get to all of that later. And then in the last case, usually it's fun to just print out a little message saying, like, enjoy your shell or something, but right before you set interactive. Trying to think, what CTF was that in? Trying to find one where I was able to like basically create functions, give it with with a really nice primitive. Just like if I had like a read anywhere primitive, I could just like create a function that did that. What's a good example of that? And they're all over the place. Don't remember a good one. Let's try Secon maybe. Jumper. Okay, yeah, this is actually a good example. Not really of the challenge, but like. Since you're in Python, if you have like a repeatable thing that you can do, say like I found a thing where I can give it an address and I can read out the stuff from that address, you can just make a function. In this case, I call it read, and so I just implemented what I want to do there. In this case, we go through a menu system a little bit, encode the address, do some other things, and then like basically it looks like we're leaking out something there, and then you can just use these all over the place. So I can just read out like an entry. I can just read out memory with this kind of stuff. And again, it's all just Python, and there's the obligatory enjoy your shell. Yeah, so it's super nice though, right? Because you can just create these primitives, simple Python functions. You just pass in, an address or whatever, and you can use your global process or whatever, and just say write to this address. And once you have that figured out, you can just do that as many times as you want. So creating these like repeatable, reliable things is really, really nice to be able to do. It makes developing more complicated exploits so much easier.
You want a fairly intricate exploit, like VF exploit from Uncle KR.
It's not on. Okay. Yeah.
That's
There's.
very intricate.
Yeah. Well, actually, let me go back really quickly and see. That was a relatively good example. Like, actually, so this exploits 112 lines of Python, right? I know I've done worse. I know there have been some ones that were easily over 200, and when you have something like this, it just makes it so much easier because you don't want to be typing in 200 lines or more of break here, enter this, go here. What's the register here? Add 10 to that. Break there. Like you don't want to have to do that, right? So this just makes it so much easier. Let's see. Let me pop open the cheat sheet that I was working on earlier to make sure I didn't miss anything. That's loud. Okay.
My exploit for VF is 160 lines.
Yeah. So I guess one other thing just to reiterate, Pwn debug does set this by default. You'll notice if I did the disassemble main, this was Intel syntax, but by default it's not. Again, the set disassembly flavor is useful because AT&T syntax is weird, and this just makes it a little bit more sane to read. So yeah, does anybody have any questions, or like how would I go about doing a specific thing in GDB, or I don't know what was all of that? Anything? Sure. So don't have a good example for this off the top of my head. Yeah, sure. Let's see. Right. So let's see if I can type while I'm talking. So GDB, you can also do, like Brennan was just saying, basically conditional breakpoints, right? So if I have something that I want to examine, but only as we go later on in the program, so say I have a loop that iterates 20 times or something, this is going to be a really, really bad example because there's nothing interesting happening. But like if I run this, wow, all of the numbers printed out, what a shocker. But if I'm in GDB and something weird does happen, that's say like the 15th iteration, and I want to break into that there, so let's get an address that we want to break into. So let's say we want to break right before printf is called. One thing here is I could actually just say break on printf and do like that, or I could break on the call to printf, excuse me. Either way, either would work. But if we want to do this after the 15th time, one thing that we do need to kind of be careful about is, how are we accessing the variable I or whatever. In this case, it does not look like that symbol is included. Or if I run, yeah, no, it's not included because it's inlined into the for loop. Anyways, so yeah, so if I want to break after 10 times or whatever, let me delete the breakpoint, break on it. What is it actually? Like I know how to do it in a script. Is it just if?
Yeah, so break printf if whatever. Or
Yeah.
you already have breakpoint, then it's con1.
That's okay, right? That's what it was. So yeah. So say we've got some other things. Get rid of that. We continue a little bit, and we realize this is going to take too long. We can like get information about our breakpoints, right? So we just know it's number 2 in this case. We might have a lot of these. And let's say we can add conditions to these. So we can say condition on number 2 if what was it? RBP minus or plus 4, I think. Let me just go down here. Disassemble main again. Yeah. So come to if. This is actually going to get kind of messy because you have to dereference it like that. Can you just do it like that? Okay, and I need the $sign. Yeah. Okay, there we go. So if we now info breakpoints again, you can see this is basically saying we will stop only if the value at RBP minus 4 is greater than 10. So if we continue a little bit, I believe. So this is one place where GDB does get kind of annoying. It's not happy about this because it's just saying this is something. We don't know what this is. So I need to tell it to dereference this as, let's say, UN32T. Now, in theory, or 64, because we're on 64-bit. Now, if we continue, there we go. So now, if we look at the memory there, so again, x slash, let's say, 5a, or let's just x/x, RBP minus 0x4, we're now at B, so this is again 11, right? We skipped from whatever we were at before, like 5 or something, probably down to 11. Or we can do this again, say if it's greater than 19, so we're on the very last iteration of the loop, minus 1 derp. Let me set the condition to be greater than 18. Now you can see, if we examine the memory, this is 19, right? So this is going to be the last iteration of the loop right before we continue. And so now we can introspect the program right as it was, or right as it is on the last loop without having to go, you know, if we didn't have that, we would have to like break on printf, run, and then we'd have to like just sit here and hit C about 20 times, which is no fun. And also you might have noticed this, if you have a command and you just hit enter, it'll just rerun the last command. It won't just like create like a new line like it does in bash or something. So be careful of that, because you can do like, if you just typed continue and then you broke and then you meant to like just enter a new line, you can continue past where you meant to, and then I've gotten very frustrated over that sometimes. But yeah, otherwise, that's more or less it. That's basically all you'll need for GDB for quite some time. Again, the main thing is just what's at this place in memory, what is my register state at this point. If you're somewhere like crazy, like if you've got like a recursive function and something's breaking, your backtrace you can see basically this walks up the stack frame or the stack frames to figure out like what you last called, what to return to. However, as soon as you start exploiting stuff, this usually becomes broken, because if you're overflowing something on the stack, it just corrupts all the information here, and GDB can't figure anything out. But if you're for normal debugging, backtrace is very useful. Yeah, so I guess any other questions, or anybody, Josh or Brennan, have anything else to show? Any ideas? Anything else to show?
What if you want to like evaluate something that involves con function?
That involves what?
Con function.
Oh, okay, so yeah, I'm not going to, only because I've never actually had to use that in the CTF. But yeah, if you do actually have symbols, GDB can do all kinds of stuff. Like it can actually like call a function and then with whatever arguments you provide, and then get the return value and give that to you, as if the program did it, but you're doing it from GDB. But again, most of the time in CTFs, you don't get symbols, and that you may still be able to convince GDB to do it, but that would not be fun to try and do if you even could. You may not be able to because of calling convention stuff, but who knows? GDB's crazy. Yeah, so I guess that's all. That's all that I've got. Josh, anything else? Okay. So next week. So Brennan's out at a conference, and Josh and I are both actually going to be playing a CTF up at University of Connecticut. So we won't have class in here next week. That said, though, we are, since it is midterm season, we are going to put up, let's say, a little bit extra homework that will be due. Basically, are we doing?
It's going to be basically next week's homework will be more problems.
Yeah.
You save 2 hours here, and instead we're gonna give you a lot.
Yeah. So. Not a lot. Let's not be over like 500 points instead of the normal 300.
Normal weeks have been 300 points of problems. Yeah. Next week your homework will be 500 points worth of problems. We'll send an email out to this effect as well.
Yes.
But
yeah, so that said, this is also going to be kind of annoying because we are not going to be here on Friday either for office hours. Next Friday, sorry. This coming Friday we'll be here. So if you do have issues with this, drop by this Friday. Or, again, we're in the lab most of the time. We should be up until around 3 p.m. on Wednesday. After that, I can't really guarantee anything. Or email always. Yeah, so let us know if you have any questions with GDB with the homework. Otherwise, I guess we will see you all in 2 weeks. So.
Also, I'll be here next Friday. So.
Okay, that's good to know. Didn't know you'd be back with them. Yeah, so I don't know, 10th floor, 2 Metro, in here somewhere up there. Yeah. So.
No, we'll have 1 week of homework and then next week we're gonna like.
Yo.
So for next Wednesday at 6, we'll need to have 300 points done.
Yeah,
And
Josh is talking about it right now. Yeah, we'll.